All right, so guys, section 2.4 starts off with this stupid little cartoon. Like I said, nobody said it was going to be overly funny or anything like that. But again, hopefully you've spent even just a couple of minutes kind of familiarizing yourself with where we're going. Today we're talking about complex numbers, the imaginary unit I. So again, this kind of ties in with where we're at. So we got a couple of numbers, 2 and 3 off in the distance. Looks like number 8 yells out, hey, you guys want to meet my new friend? And they reply back, sure, but where is he? 8 says he's right here, and then he questions his new friend, why can't anyone else see you? And so why is that? Why can't anyone else see him? That's, again, another interpretation. Or we could look at this as the square root of -1. That's the imaginary unit. So, again, it's an imaginary friend. You guys get it? Like I said, nobody claimed it was going to be funny, but that's a little funny, I guess. It's a math joke, you know. You gotta take it with a grain of salt, so to speak. You can't have too high of expectations. I mean, it's a math joke. So anyway. All right, so guys, today we're going to be talking about complex numbers, something that I know that you have seen before. To what degree? That's the question, I suppose. And the reason why I say that is just that sheer fact that, COVID changed some things for sure. Now, I think that where you guys were at last year in Algebra 2, I think things were. The attempt was to be somewhat back to normal, but this was a fourth quarter Algebra 2 concept. So if you could think back to that 1920 school year, Algebra 2 students just simply didn't get this. So those students who came to from Algebra 2 that year came to pre-calc that next year, this was brand new stuff. So if my memory serves me correctly, last year wasn't completely brand new stuff for students. We were kind of getting back into that realm. Now, I say brand new stuff just because realistically, yeah, they probably were supposed to watch videos or something like that over the quarantine. Hi. This is for me? Yeah. Do you have any idea what it's for?
You're listening to some sweet too.
Thank you. I have a feeling these are not meant. What would I need with 25 sets of headphones? Oh gosh, that's a lot. Okay. All right, so back to this though. Complex numbers, I'm pretty confident when I say that I think that you've seen these before. The imaginary unit, that's kind of where we're at. Good news though is that even if you were absent or you forgot most of this stuff, we're going to cover it in a way such that you're not going to feel behind whatsoever. So one of the things that you'll see on this first slide, this is just kind of that hierarchy of numbers. We're definitely living within the rational numbers way more often. That's the one thing that I maybe dislike about this graphic is that it kind of seems like we're using certain types of numbers more often than others, and that is not necessarily true. Again, we're within the rational numbers the vast majority of the time, but technically everything's under that umbrella of what we call complex numbers. Even though we have, and we'll talk about it here in a couple slides, if you just have an integer value, it's still technically complex, because you could say plus 0i if you really wanted to. Like I said, we're really stretching at that point, but it does hold true. All right. So the goals that we have for today: number 1, we want to be able to add, subtract, multiply, and divide complex numbers. Add, subtract, and multiply, I would confidently say that you covered the heck out of that last year, most likely. Now, to what degree we remember it, time will tell. The division of complex numbers, that's going to be one of the places that we want to focus. But it's not really dividing in the sense like anything like what we were doing with synthetic or long division. It's really just that when we have a complex number that's in fraction form. We have a numerator, we have a denominator. Technically, fractions are division problems, so how do we clean that up? Basically, long story short, we can't have an imaginary unit in the denominator. Like, it's not allowed. It doesn't exist out there. So how do we actively get rid of it? How do we take those necessary steps? And that's what today's going to be about, or one of the things today's going to be about. Second goal, we want to be able to reduce powers of I. This may be something that we remember how to do immediately. It may be something we need a little bit of coaching on, but again, reducing powers of I is going to be important for us. And then goal number 3, we want to be able to find and use complex conjugates when we're interacting with complex numbers. I would say that goal 3 ties very closely to the division aspect of goal 1. But if those words are not, or those phrases are not ringing any bells, don't worry. Once you see a couple of examples, I'm confident that it'll start to make sense again. All right. So what everything is essentially hinging on today is this concept that we can't find the square root of a negative number. Okay, we just can't. So I know that I'm going dramatically out of order here, but what if we wanted to solve an equation like this? If we had x squared plus 9 equals 0, we know that we're going to subtract 9 over, at which point now we have that x squared is equal to negative 9. And when we square root both sides, of course, plus or minus, we have x equals plus, and then we run into problems. So without imaginary units, or without the imaginary unit I, we would have to say this does not exist, can't go any further, we literally cannot find the square root of a negative number. Like there's no real number that's going to be associated with the square root of a negative, because it doesn't make sense. How could I possibly multiply a number times itself and get negative anything? It doesn't work, doesn't happen. That's, again, introduce the imaginary unit I because mathematicians, I'm assuming hundreds of, not thousands of years ago, they started to grow sick and tired of having to stop here. Can't we go a little bit closer? Can't we be a little bit better? Because what this essentially is doing, again, would you agree, going back to the beginning, x squared plus 9, that's just our parent function parabola, which is about 9 units. And what we're trying to find right now, without actually saying, where does it cross the x-axis? Short answer is that it doesn't. But it does have imaginary zeros. Does that make sense? Again, they're not real zeros. We can't literally come over here and put a point on the axis. Okay, it doesn't happen. It's not physically crossing the line, but we still want to be able to identify the imaginary zeros. So the way that we're going to do that is that we want to think about splitting this apart, the square root of 9, square root of negative 1. Everybody agrees with that separation? Okay? And then hopefully you're confident with the rest of this. What's the square root of 9, please? Plus or minus 3. The square root of negative 1, we said that. So that's what we're going to be able to do. Hopefully that's what you remember doing in past years. But like I said, all of this hinges on the understanding that I represents the square root of negative 1. Okay? So if I is the square root of negative 1, let's not overthink this. If we had the square root of 3 and we squared it, aren't these inverse operations, the squaring and the square rooting? So wouldn't we just be left with the 3 that's in the interior? Isn't that how that works? So my question too, would that be any different if we have the square, or if we had I squared? Okay, remember what I represents. I is square root of negative 1. If we square that, what should we expect to get? We should expect to get negative 1. Does that make sense? Okay. Now I cubed is another one that, again, if we allow it to be more complex or more complicated than it needs to be, again, I suppose this could be spun around to where things seem confusing, but we can look at it this way. I cubed, that's the same as like I times I times I. Well, what's I times I? What's that? What would we call that again? That's just I squared. And what's I squared again? Negative 1 times I. We're looking at it that way. It seems pretty clear then that I cubed is really equivalent to just negative I. Okay. Same logic. What if we had I to the 4th? Let's do it the lazy way. What if I just add another I in here like this? Okay. Well, wouldn't that just be like I times I is I squared? So, whoa. Try not to erase things. I squared like that. And at this point, what's negative 1 times negative 1? Okay. Now you'll notice that we stop here. Why don't we go I to the 5th, I to the 6th, I to the 7th? Because in theory, we could do this infinite number of times, right? But it's a loop. The pattern would continue. If we had I to the 5th, that's the same as I to the 1st power. Why? I'm saying that I to the 5th is the same as I to the 1st. Okay. The reason for that is I to the fifth is really I to the first times I to the fourth, and if we can get any multiple of I to the fourth, isn't that just 1? Okay, so one of the things that you may be asked to do on tonight's homework would be something like, what is I to the 203rd, or something like that. Okay. On the surface, this might seem confusing, but couldn't we just break this into, if I could break this exponent into some increment that's multiple of 4, I don't know, maybe I to the 200 times I to the third. Well, what's I to the 200? Again, talk about overdoing the problem. Would you agree that's like I to the fourth 50 times? You would not be expected to write it out this way, but does that make sense, what we're saying? And what's I to the fourth? It's just 1 to the 50th power. Isn't that just going to say 1? And all along, we still have this I cubed business. And what did we say I cubed is? It's just the same as. If you want to put the 1 in there because it makes you feel better, that would be okay, but I would say that's unnecessary. Just implied, for sure. I would have a hard time saying, no, that's wrong. You shouldn't have that coefficient of 1 in there, but I would say in simplest terms, just negative I. William. So anytime you can take out 4 of them or increments of 4, it's just whatever you're left with. So I to the 6, well, I can take 4 out of there. I'm left with I to the second. I to the second is negative 1. All right. So guys, that's going to lead us to what we call standard form. So standard form, very important that we're understanding, is going to be A plus BI, where A is the real part, the BI is the imaginary part. So it's always, every single time that we have a solution of any sort, has to be in this standard form. The real plus or minus the imaginary. So last slide, we had the plus or minus 3i. We said that was the answer. Is that in standard form? Because it doesn't completely look like it follows the pattern of A plus BI. But is it in standard form? Yes, it is. We can think about this as technically 0 plus 3i or 0 minus 3i. If we really had to be in that physical format, there it is. That's what it would look like. Okay. One of the things that we talked about previously, integers. What if we just had the integer 7? Is that in standard form? Sure. It's implied, I guess, that if we needed to, we could write that as like 7 plus 0i. Now, I can't think of any reason why anybody in their right mind would prefer to write it as 7 plus 0i instead of just 7, but technically it's true. It stays consistent. All right? So I'm okay with, you're okay with it, I guess, saying that 7 is in standard form, or 3i is in standard form. Again, we know that that's going to be standard form. We can't be any better than that. All right? Okay, so these complex numbers, again, it's going to be a set of all numbers that are in that form of A plus BI, or could be put into that form A plus BI. It's got to include both the real and the imaginary numbers. The biggest mistake, of course, is people flip-flop those. We put the imaginary first, the real second. It has to go in the correct order. Real number plus or minus imaginary. Questions? No? All right, so when you walked in the door today, adding and subtracting and most of the multiplying, I'm sure that we could just rattle through this stuff. Even if you don't quite remember it from last year, your knowledge of combining like terms is going to get you pretty far here. So especially when we're talking about adding and subtracting these complex numbers, we know how to combine like terms with the x's and the y's and the z's or whatever variable you may have. It's no different. I want to be clear when I say this, so I is not a variable. It's an imaginary unit, but we treat it just like a variable. We're gonna group things. I cannot add imaginary numbers with real numbers, but I could add two imaginaries together, and we can obviously add two reals together. So if we wanted to add or subtract the real and the imaginaries, we're just going to do it separately. So right now in this particular problem, we know that 7 and 5, those are the real aspects. 7 plus 5 is 12. We're going to add the imaginary portions. 3i, negative 4i, what's that going to be, please? Negative 1i. So to really solidify this, 12 minus I would be our solution. Okay. Same thing for that second example. The only difference here is we just have to distribute our negative through. So realizing that we really have 4i plus 3 minus 5i plus 2 minus 6i. Now when we combine, Real portion first. 3 plus 2 is 5. 4i minus 5i is negative.